Hey everyone, my name is Ramon and I'm the team lead for the Software Supply Chain Security CTF and Codelabs. Our team was tasked with creating a CTF around software supply chain attacks. We essentially just simulated various attacks along with creating a code lab per level that acts as a guided walkthrough. These sorts of attacks can be broken down into 4 primary categories, which we defined as compromising the development process, compromising the developer tools, compromising packages included into an application, and deployed an out-of-date runtime that can be compromised.
Our CTF is played through various Docker containers. Each image here contains some component of our 11 different levels covering various software supply chain attacks. The containers are accessible here, but users don't need to access this page to download them. Instead, each level is accompanied with a code lab. The code lab serves as a walkthrough of setting up the level, performing the exploit, finding the flag, and then finally tearing down the level. Our code labs also contain background info on the attack, as well as the learning objectives. Let's learn how a software supply chain attack works by playing one of our levels. In this level, the goal is to modify a public repository and inject malicious code in order to retrieve someone else's environment variables. Here, we have a website, get_t, that is being hosted locally on a Docker container. Looking through the website, you'll see that the only available repository is Python's Flask package. If I could gain access to a developer account of this repository, I can covertly inject malicious code that grabs your computer's environment variables, packages them in a network request, then sends it over to my machine. I'm going to attempt to do that by breaking into this developer account, Pallets, using a password cracker. When I say my machine, I really mean my interactive Docker container. In most cases, our levels come with a Docker container that serves as the environment for the player to mess around in. And these come packed with everything needed to complete the level. Here, I'll execute a somewhat complicated command that performs the password crack we need. The steps to take and the details of creating this command are gone over in our code lab. And after about a minute of brute forcing, I managed to find Pallet's password. It's pretty weak. From here, I can log in to Pallet's account and have full reign over the entire code base. This is already bad enough, but we can extend the damage further by injecting some malicious code into the Flask repo. Let's do just that by cloning the repo and making some changes. Here, I found a good spot to hide the malicious code. My goal as an attacker is to let this code sit in the public repository for as long as possible. So it's worth taking some time to place my code in an inconspicuous location. This code will attempt to make a request to my machine, hostname Ubuntu, and then send over the current machine's environment variables. From here, anyone who executes this code will send potentially sensitive information directly to my machine. After bumping the version number and then committing the code, I can use Pallet's password to push my new code directly to get_t. And here's the commit. Nothing seemingly out of the ordinary, other than it was performed without a pull request. With the malicious code in place, I'm going to start up a simple socket server. This will listen for and accept any incoming connections from those that execute my malicious code. After some time, someone makes a connection to my machine and sends their environment variables. We can see an SQL URI environment variable with a password exposed in plain text. Along with that, we can see the levels flag. The remaining 10 levels of our CTF explore the various ways software supply chain attacks occur in all sorts of different environments and scenarios.
So as a brief project overview, we made a set of capture the flag levels or scenarios around the concept of software supply chain security. In each one, players were challenged to achieve a certain objective, and through completing that, they'd wind up with a text flag they can point to as evidence that they finished. For a target audience, we expect our players to be at least as knowledgeable as the typical upper division computer science student. We're not targeting only students. We want this to be useful as well to, say, people in industry who want to brush up on their skills, but we're assuming that level of experience is a baseline. The collection as a whole we actually want to be useful as well to educators, to professors who might want to use this to help teach the concept of supply chain security to their students. Our primary features include 11 different capture the flag levels, as well as a setup guide for the player. We made these have minimal upkeep for, say, an educator who wanted to host these levels themselves. We included walkthrough guides for every single level, and we also included some extra explanatory material to expand on these concepts a bit. Here's a list of all the CTFs that we created. I won't read them all off, but you can take a look, and they cover a wide variety of topics. For minimal upkeep, what we did was any capture the flags with server requirements. So say the player has to push something to a server, or the player has to break into a server, that sort of thing. All of those server processes will run on the player's machine. So there isn't anything that has to be hosted by us or by an educator. This keeps these upkeep requirements low. It makes the architecture a lot easier to understand and a lot easier for us to develop. And ironically, it means we don't have to worry as much about the security within our CTFs themselves. For every single CTF, we created a text walkthrough using Google Codelab. These would be simple guides that would help the player through these levels in case they got stuck or in case they just wanted to see the intended solution we had for these levels. We also use these walkthroughs to help add some narrative context. Many levels will have the player being a member of a fake company or trying to attack a fake company. And we can use these Codelabs, these walkthroughs, to introduce that concept a little bit better than within the level itself. With these Codelabs, we also included supplementary material with many of our levels. We'll often link to external resources or to specific documentation pages. And we can just generally use this to expand on the topics in ways that we might not be able to do in levels, in ways that might be hard to gamify or hard to represent.
I'm Catriona McKay, and I will be going over the additional features of our project and what we possibly could have done in the future. Our CTFs covered 4 different types of supply chain security attacks. Compromised developer tool attacks focus on exploiting weaknesses in developer tools. We made a CTF on the VS Code Python extension exploit found in 2019 that allowed code in a virtual environment to be executed without user knowledge. The second type of supply chain security attacks were attacks on the developer process. An example being gaining API keys for sensitive information. Our compromised developer workflow CTF emulated the Code Cove breach from earlier this year. The next type of CTF is compromised packages. There are many ways a package can be compromised, such as a malicious contributor, a package that had been abandoned, or a typo-squatted package that was used in an application. We also had CTFs that showed how deployed and outdated code could be used for an attack. Our frozen dependency CTF demonstrated how known and patched CVEs could be used as an exploit if an application had a frozen dependency to a version of a package with said exploit. If we had more time, there are a couple of features we would develop. The first would be more CTFs. This would broaden the knowledge of the people completing our CTFs. We would focus on compromised developer tool attacks since we only have one CTF of that type. Next, we would implement a higher level application to set up the Docker images so the user could set up all the CTFs at once. After that, we would improve some of the dummy application websites used in the CTFs. For most of the CTFs, the dummy applications resemble usable websites, but for a couple of the websites, they are the bare minimum for the CTF to work. Finally, we would create a website to host the CTFs. In the beginning, we were given an example collection of CTFs called Thunder CTF that had a website to walk the user through the CTFs for those who didn't have Codelabs. We would have liked to implement a similar website.
All right, hi, I'm Elizabeth, and this is architecture. Due to the great variety of our CTF levels, we're only going to cover a broad scope overall look at the tools we use to make the levels. For our basic architecture, we used Python as our programming language, Flask as our web framework when necessary, and Docker to set up player environments and host web services. Now, Flask was not used in every level, but it is present in most of them, including the Bitcoin stealer, typo squatting, frozen dependencies, compromised developer workflow, and compromised developer account. We used it for many things, including as a server, listener, and even a client application. Next, Docker. Docker is OS level virtualization software, sort of like a virtual machine. And Docker, unlike Flask, was used in every level and served as the backbone of this project. Specifically, we use Docker containers to run server and client applications and to emulate PCs in order to create player environments. In some levels, we even use Docker to host package repositories, such as PyPy and Git. When levels use multiple containers, we use Docker Compose to launch them and Docker networks to allow them to communicate with each other. Here, we have a list of levels which used single containers and which used multiple containers in a network. Notably, a few levels did not use networks, those being internal dependencies, which used links instead, and confused dependencies, which had no network or links.
Hello, everyone. This is Evan Brunswick. I'm here to talk to you about the development process, or the how we did it of how we did it. To start off, I'm going to go ahead and talk about the old process for a little bit. So we started working off individually in an agile process. We weren't really following Scrum. What we were doing is we just had a bunch of issues for each level, and we were working on each one individually. This wasn't really working out for us. After about 2 to 3 weeks of development, we determined that it wouldn't be sufficient. We were coming into meetings without having done much work, or not having much to talk about, or just plain out saying, hey, I haven't done much work since the last time we met. So we determined as a group that we needed some change and something to keep us working and to stop us from procrastinating. So for the new development process, we ended up changing our process quite a bit. Everything got recorded on GitHub issues. We split it up into 4 teams of 2 people each, and each team would handle 1 level at a time until completion. We also adopted a Scrum framework, having meetings on our agreed days, and we would also have stand-up on every other day. We would work on issues in 2-week sprints and meeting twice a week and reviewing what went well, what was finished, and what was pushed into the next sprint. We also merged all of the projects into one centralized repository, and all of the uploaded code was to be put there. And this was all meant to keep us accountable for our work and allow others to see our progress. For each level development, our Capstone project isn't like a normal project. Most of the levels that we have are completely independent of each other, starting from the design process until the completion of the level. We did agree upon key principles such as the language used, the framework used, and the deployment method. These were Python for the programming language, Flask for the web framework, and Docker for deployment. Any additional tools used on each level were used on a per level basis. For the design flow, the normal design flow would start off with an idea for the level. These ideas mostly came from articles provided by Professor Wusheng. Others came from knowing what a supply chain attack is and then designing the level around that. Most of the levels were designed from articles which show how to perform the exploit. Most of the design process was to determine how to replicate it in a safe manner for the user and also alter the level if parts of the reproduction process could not be performed naturally or in a safe manner. After design was all said and done, the level owner would then run the idea by the team and hash out any possible issues. After this, the teams of two would have free reign and would develop the level until it was in a demoable state. The owners would then demo their level to the team, and they would resolve any questions or concerns, and then they would create a code lab, which is a document that guides the user through the level and explains the level itself. Once the code lab is finished and the level is finalized, another member of the team of the overall team would proceed to record a run through of the level, and this recording would then be sent to Professor Wusheng for review. After Professor Wusheng reviews the level, he would make recommendations or suggestions for implementation, and the owners would then implement those changes, and then the level is considered complete. A pre-built image will then be uploaded to the team's Docker Hub account, and the code lab will be put into a finalized directory to be uploaded to a website later. And this whole process is done for each level.
Hi, I'm Cyrus Rice, and I'm going to be talking about our team contributions and roles throughout our project. So for our levels, we worked on each of them in pairs of two. Me and Hoy worked on the abandoned dependencies, the malicious contributor, and the internal dependencies levels. Caspar and Evan worked on the Bitcoin stealer and the frozen dependencies levels. Ramon and Jacob worked on the compromised developer account and compromised developer workflow, as well as the software bill of material levels. And then Jaina and Catriona worked on the dependency confusion, typo squatting, and VS Code exploit levels. So as far as roles went, Ramon was our team lead. He was guiding us throughout, kind of making sure that everyone was on track and chatting with our contact, Wu Chang, who was sponsoring the project. And we also had Caspar and Evan as our code lab editors. They were kind of making sure each code lab had a uniform format and it was proper with spelling and grammar. And then everybody participated in testing each other's levels and making recordings, which we sent to Wu Chang to get his feedback on. And then Catriona is also doing the video editing for the final presentation, getting all of our parts together and making the video look nice. And that is it for the roles and contributions.
Hi, my name is Hui. I'm going to present unexpected events that happened while we were developing this project. At the beginning of the development, we were thinking of creating a high-level Python application for the user to set up and tee down levels due to the nature of our project. However, after discussing with our client, it was against our ideas. Therefore, we had to remove some of the Python application code that we had been working on. Another issue is that because we had 4 teams, each responsible for crafting their own levels, it was inevitable that there was going to be crossover between the ideas of the levels. This obviously happened to us. We dealt with it by discussing how we could differentiate the levels to a point where there was a clear distinction about the context and the learning points between them. Not only did we run into similar ideas for the structure of a level, we also ran into a similar problem regarding the tools that we would use for the level. Specifically, one of our levels used a brute force method, which is using a password cracker to gain unauthorized access. Accidentally, another level had the same ideas despite different contexts. One is accessing into developer's account and one is accessing into the admin server account. But our sponsor preferred if we could find a different approach for gaining access for the second level. Then we ended up using another common way for gaining unauthorized access by letting the second level use a generic password, which is easy to guess. In a development process, it is really tricky to assess exactly the time or effort required for the level. We ran into a few scenarios where we thought that we understood everything that might be involved in setting up of the level, and it seemed simple enough. However, this was not always as we expected. For example, one of our levels, Frozen Dependencies, is about exploiting CVE, which sounded pretty easy to implement. However, it didn't go explain. We attempted to set up and execute the exploit, but ran into some issues very quickly. We were eventually able to brute force a combination of configurations and eventually reproduced it. We thought it would only take a couple of hours, but ended up taking 3 days, which were much more than we expected. So those are unexpected events that happened to us throughout this project.
Our sponsor was Professor Wu Song of Portland State University. We had 3 questions for him. Let's see what he had to say.
It's gone really well. The communication with the team and the incremental progress on each of the levels, it's been a really good iterative process. And I've learned a lot, actually. I've learned a lot from the development of this CTF, some intricacies that I had no idea about ahead of time. Yeah, it was an excellent experience on my end, at least. I did appreciate the every couple of weeks check-in, and then being able to see the incremental levels, the progress on the incremental levels. Some of the earlier ones, we were able to do multiple iterations because there was enough time to go back and twiddle with these things. So I think that, and the code labs as well, we've iterated multiple times on, and that has really improved, I think, the quality of the code labs and what eventually the students will get out of this doing these exercises. So yeah, I think it's really well done. I think it's really polished. These levels are much more polished, and they're hopefully going to be fun to play. I am not quite sure if there's an entire course of work in this. But it might be integrated into an advanced cloud and DevOps kind of course. So really, this is the pathway. This is towards the edge of what students can eventually learn in an undergraduate program. And so an advanced topics course where these would be exercises within that course is something that I've considered. Just because of the importance of supply chain security. This is something people just need to see examples of this, be aware of it, because it's one thing to read an article about supply chain security, and it's quite another thing to see how it's done, how the complexity of the package system, the complexity of the containers and the infrastructure that we're running, and then how you would having students be able to see how you can slip in anywhere and compromise a system. I think that's just going to be really valuable. Whether or not I have a whole course that can look at just that is a question, but eventually I'd like to do an advanced course that does cover these topics, and these code labs will be invaluable for that.
This is Jacob Bickle again, and I wanted to take a few minutes to talk about some of the stuff we learned over these past 6 months. And it was quite a journey. We learned a lot about some of the technical stuff, such as creating and running Docker images, as well as using Docker networks to communicate between these containers, as well as understanding various software supply chain attacks. These are all really helpful skills that we can take with us outside of just school and security related fields. But however, we also learned a lot more about everything that goes into creating software with a team and a client. First, a ton of planning has to go into it. You have to get user stories from the client, have a chat with the team about them, and then clear things back up with the client and rinse and repeat until you've got a feature set. On top of that, in our case, we had to plan out each level beforehand and put things to paper. The team and then our client would take a look at it and make any comments and adjustments, and then only after all that work is done, can we actually utilize our technical skills to create a level and pull it all together. This process is a far cry of the majority of the previous 2 to 3 years of college, where little planning at all is required to create a project because it is almost entirely well-defined. Additionally, we also learned pretty quickly how important asking for help on a task is. As software engineers, we love to solve problems and want to figure them out for ourselves. It's a lot of fun to do that. But a few times we got hard blocked on an issue and dug into too many rabbit holes before asking for help. And then only then to be met with an instant answer because someone else has run into that same problem before. It's really important in moments like this to utilize your team. Everyone has different experiences and has solved all kinds of problems. So asking for help is the most effective way to put our various backgrounds into use. Some advice I'd like to give to the next set of Capstone students is to start as early as possible. You'll want to utilize all the time you have, especially if the project is less well-defined. This is because scoping is really hard. Even after 4 years of scoping project work, I personally still find myself biting off way more than I can chew. Starting early allows you to figure out what works and what doesn't quickly, as soon as possible. This allows the team to narrow down to a more reasonable project deadline and feature set. The saying, fail fast and fail often, applies here in a very literal sense.
And that is our presentation for the Software Supply Chain Security CTF and Code Labs for the Computer Science PSU Capstone project. We'd like to give a big thanks to Professor Wu Song, who was a great sponsor of the project. Thank you.